I want to return to the orbital picture a little bit in this video and recall that we were talking about the 1s orbital and the 2p orbital. And in this video, I want to talk about how those atomic orbitals can combine to form what are called molecular orbitals. And in the process of doing that, we're going to see that they can form what are called sigma bonds and pi bonds, and we'll talk about the differences between those two. In 1923, de Broglie suggested that the properties of the electrons are better treated as if you treat electrons as waves rather than particles. Now we know the electron is a particle, but it also has a wave nature associated with it, so it sort of has that dual nature associated with electron. And the way we can think about that in terms of something that we can understand is treating the electron like the standing wave of a guitar, which Wade talks about in the textbook. If we think about a guitar string and we pluck that guitar string is going to be displaced either in an upward displacement or in a downward displacement. And you can see that here. So at one moment it's going to be displaced in a positive direction, and another moment is going to be displaced in a negative direction. And so it's alternating, and it has that wave nature associated with the guitar. So the electrons are much like that. Now if we apply that to the 1s orbital, and we treat it like the fundamental vibration of a guitar, you can think about the wave function of that 1s as either being at one instance positive, which is shown here, or at another instance as being a negative wave function. So it has a sign associated with that wave, just like a wave in the water has, right? It's either one instant is positive and another instant is negative. And we can think about that as a spherical 1s orbital here with a positive sign, or a spherical 1s orbital at a negative sign at some other instance in time. Now it's important to realize that the positive and the negative here do not refer to the charge of the wave, but simply a mathematical sign associated with that wave function. If we take the wave function and we square it, that's psi squared, it's actually going to give the electron density associated with that wave function. So we're going to see that if we square psi, we can actually get the electron density as a function of the distance from the nucleus. And you can see that the electron density increases. This is for the 1s orbital. And then as it gets to the nucleus, it reaches a maximum, and then the electron density decreases. So if we apply this concept to let's say the 2p orbital, let's say of a carbon atom, the way you can think about this is if you're putting your finger on the fret of your guitar and then you're plucking the string, right? And we think about this, here's a wave, there's actually two waves that are set up here. There's a negative displacement on one side of your finger, and there's a positive displacement on the other side of the finger. And this would be the harmonic of the guitar string here. And what you have then is in terms of an orbital, it would be where your finger is a region of zero electron density, right? The string is not moving there. And so it's only negative displaced or positive displaced. And at some instance later, this becomes positive, and this one over here becomes negative. Now, if we think about the 2p orbital, it's sort of like this. You have two lobes that are separated by a nodal plane, right, where there's zero electron density. And at one instance, the two lobes are out of phase with each other. So we have a negative and we have a positive. Again, at some other instance, it's positive and negative. And if we think about that, that can kind of resembles the dumbbell shape of the p orbital here. So at one instance it's positive on this side, is negative over here, and then later on it's positive and it's negative. So it has that alternating phase that that is a wave function for that electron. So we want to talk about these atomic orbitals, the s orbital and the p orbital, and how they can be combined to form what are called molecular orbitals. So atomic orbitals can combine and overlap to form these more complex standing waves, which we will call molecular orbitals. And we can add and subtract their wave functions to give the wave function of a new orbital. So we're going to talk about the guidelines for combining atomic orbitals. Atomic orbitals on different atoms combine to produce molecular orbitals. And the key phrase here is they're on different atoms. So if you had a 1s orbital on one atom and a 1s on another atom, those could combine to form a molecular orbital. The other thing that's important here is that they're going to form what are called bonding and anti-bonding molecular orbitals. And this whole process of combining these to get the bonding and anti-bonding molecular orbitals is called a linear combination of atomic orbitals, or LCAO. So you can mathematically describe that like this. If you have a molecular orbital that is resulting from the combination of atomic orbitals on the individual atoms. So you have some coefficient out in front of these atomic orbitals which gives it a weight, and you add those together and you end up with a new molecular orbital. Another important guideline is that each atomic orbital results in a molecular orbital. So for example, in this case, if I combine 3 atomic orbitals, then really I should get 3 molecular orbitals that are resulting from that combination. So not just one, but an MO1 and an MO2 and an MO3 coming out of the combination of 3 atomic orbitals. And then finally, when atomic orbitals are combining on the same atom, not on different atoms, but on the same atom, then they're going to produce new atomic orbitals that are going to be called hybrids. And we'll talk about that in the next video. So returning to the covalent bond and how these molecular orbitals form from atomic orbitals, the electrons in these molecular orbitals are actually going to occupy space directly between the 2 nuclei. And if you think about that, that's actually what holds those nuclei together. And if you have a positive nucleus and a positive nucleus, obviously those are going to repel each other. But those electrons that occupy this space are actually masking the positive charges, keep them from repelling each other, and actually cause them to be an overall attractive force between each other. But it's those electrons right in this region that are allowing those to bond to each other. And when you have electrons right in that region between the nuclei, this is going to be called a bonding molecular orbital. And it places a large amount of electron density right between the 2 nuclei in what is called the bonding region of that molecule, or the bonding region of that molecular orbital. We can imagine 2 1s orbitals coming together for 2 hydrogen atoms. And if we think about it, if they are in phase with each other when they come together, as they are here, they both have a positive phase and a positive phase. That means that they're going to constructively overlap to form a bonding molecular orbital. So positive plus positive gives you a new molecular orbital that's called a bonding molecular orbital. And what does that look like? Here are the 2 1s individual atomic orbitals, and when they combine, they give you this new molecular orbital with a high electron density right between the 2 nuclei. In fact, most of the electron density, lies on a line that connects those 2 nuclei. And when we have that, and it's cylindrically symmetrical, like this one is, you're going to have what is called a sigma bond. So that is a sigma bonding MO that's forming between the 2 hydrogen atoms when they combine, when they are in phase with each other. So what about when they are out of phase with each other? When we have 2 1s orbitals that are combining when they're out of phase, they're going to interact destructively, and they're going to form what is called an anti-bonding molecular orbital. So here you have a positive phase of 1s and a negative phase of a 1s combining, and you'll notice that there's a cancellation right here when these 2 combine, and that's actually going to give you a node in the molecular orbital where there's 0 electron density. We were talking about nodes earlier. So when that happens, what you have is the formation of an anti-bonding molecular orbital. And an antibond means exactly that. There's very little electron density between the 2 nuclei. In fact, most of the electron density is away from that on either side of the nucleus, but not in between the 2 nuclei. That's an anti-bonding molecular orbital. We can represent that as a positive phase of a 1s interacting with a negative phase of a 1s, and then we get this kind of anti-bonding molecular orbital. This is sometimes called a sigma star, where they put a little asterisk on there to indicate that's an anti-bonding interaction. It's going to be higher energy than a bonding interaction. So here is a energy diagram of that situation we were just talking about, the formation of a bonding MO and an anti-bonding MO. We have a 1s atomic orbital combining with another 1s atomic orbital. This is energy in this direction. When they come together, they're going to form two molecular orbitals, because there's two atomic orbitals. One of them is going to be bonding, and you can see that here. That is, the electron density lies right between the two nuclei. And then there's also going to be the anti-bonding molecular orbital, which is going to be higher energy, as you would expect. And that means the electron density is away from the two nuclei, and you're going to end up with an anti-bonding MO. Now, in the ground state of the hydrogen molecule, the two electrons that you have will be in the bonding molecular orbital, and there will be no electrons in the anti-bonding molecular orbital. But of course, that doesn't mean it doesn't exist. The anti-bonding molecular orbital does exist, and if we give that electron some energy, we can promote it into an anti-bonding molecular orbital. But of course, if that happened, then the molecule would fall apart. But that's what would happen in case of promoting an electron into that anti-bonding MO. So we have both a sigma and a sigma star.